Okay, so we'd left off there. And now, to test our brains after a week and some change, consider this non-spontaneous reaction. Based on conceptual reasoning, which of the following best explains why molecular iodine does not oxidize bromide? Is it that bromine is more electronegative, therefore you do not expect bromide to give up an electron to iodine? Or is it that iodine is more electronegative than bromine, therefore you don't expect iodine to give up an electron to bromide? Or is it that one's in solution and the other's solid? Iodine is more electronegative than bromine? Is it? It's not, I don't think. Bromine is more electronegative than iodine. It's closer to fluorine. That's one way that you could tell. Or if you remember the mnemonic Fonkel-Brick-Ship, F-O-N-C-L-B-R-I-C-S-H-I, no I, because we used I earlier, and then P, Fonkel-Brick-Ship. That's the order of the most electronegative elements. Bromine comes before iodine. So it's A, we don't expect bromide to give up an electron to molecular iodine. You may recall that the change in standard Gibbs free energy is equal to negative ideal gas law constant, or just whatever this is, T natural log of K, our equilibrium constant. And we also have the same thing, delta G naught equals negative NFE, where F is the Faraday's constant. We can set these two things equal to each other and relate the standard electrode potential of a cell to all of this other stuff. So we're going to move the negative NF over to the other side. We get RT ln over NF. And a bunch of these are constants. So R is a constant, F is a constant, T is not a constant, but if we consider it at 25 degrees Celsius, then it's a constant. And we can change our natural log to our base 10 log. So there's a bunch of fun information down here. So units-wise, we've got joules per mole Kelvin from our R. Our temperature has units of K. So those will cancel. I'm just showing you the units because we got the number stuff written down below. We do a change of base from log base E to log base 10 with this whole thing. You don't need to know how to do this. It's just showing you where this equation comes from. And then we have N, which is the number of moles of electrons, and our Faraday's constant, which is coulombs per mole electron. And I think those cancel. So we're left with joules per coulomb, and joules per coulomb equals volts. So we can condense all of this down into this shorter, nicer equation to relate the two things to each other. So we just expressed a bunch of our constants as their numbers and then crunched them all down, and we get this 0.0592 over N times log K. Log K because it's just a little nicer to use log base 10 rather than log base E. So let's use that information, that new equation. I'll write it down for us. The standard electrode potential of the cell is equal to 0.0592 volts over n, the number of moles of electrons, times log base 10 of K, our equilibrium constant. So let's use the tabulated electrode potentials to calculate K for the oxidation of iron by H plus at 25 degrees Celsius. So we're trying to find K. That means that we need N and our standard electrode potential. How many electrons are transferred in this balanced equation? 6. How did we get 6? Yeah, so we have a total of 6 positive charge from our irons, whereas we had 0 before. And our H's, or our protons, had a 6 plus overall and went to a 0. So there must have been a swap of 6 electrons for those charges to swap. We could also find, and indeed we have to find, down here in our reduction half reaction table, it's our second entry just below our standard hydrogen electrode, SHE. We've got our iron 3 plus going to neutral iron. And we can see that we've got 3 electrons transferred there. But we have a coefficient of 1 in front of our iron 3 ion and in front of our metallic atomic iron. So we could also just see that we've multiplied that by 2 and we've got 6 electrons transferred. Okay, so N equals 6 moles of electrons. And what about our standard electrode potential of the cell? What's one of our half reactions and its E value?
The iron one.
We've got the iron one. It's a negative here. Is this the same direction that we have in our equation?
That should be reversed.
It's reversed. What does that mean that we do for our E value?
Make it positive.
Yeah, so we make that positive. So it's positive 0.036. How about for our other one?
Okay, do it one at the top.
Yeah, it's the hydrogen one at the top. And so it's a 0, because that's our reference half reaction. So that's automatically 0. Do we do anything with our electrode potential when we multiply it by 2 for our balanced equation? Yes? No? Guesses? We do not. We don't do anything. Multiplying by 2 does not change our electrode potential. So we just leave it at 0.036. So our standard electrode potential of the cell is 0.036 volts. Now we've got everything that we need to calculate K using this equation above. It might be helpful to rearrange a little bit. So we'll have N times electrode potential over 0.0592 volts equals log K, the thing that we want, I would recommend doing this as a step. So find out what this whole left side is. So 6 times 0.036 divided by 0.0592. That's 3.648 dot 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 equals log k. To get k by itself, we do the anti-log, 10 raised to the power of whatever. So k equals 10 raised to the power of 3.648 dot dot dot. Which is 4.5 times 10 to the 3. Or 4,452.958514 is maybe what you'd get in your calculator. Questions about any of those parts?
And why not you multiply by 2 for the E value?
Because we don't. It has to do with, I think that's a couple lectures ago, but that's, I think it's probably just easier to memorize that we don't change it. You just flip it positive or negative, but otherwise you don't mess with it. It has to do with something about the way that the atom is produced, and you're just changing the amount of the atoms that you have. That doesn't change like the innate potential that they contain, like the potential energy that they hold. Doesn't change if you've got a billion of them versus just one of them. That's like the best way that I can explain it at the moment.
I have a question.
Yeah.
For N, I know that it's the 6 moles of electrons.
Yes.
Would that ever be different? Since I know we have 6 H pluses.
Yes.
We have the 6 from the iron.
So N does change depending on which half reactions you're mixing together.
So I know our half reactions have the same amount. Would they ever be different? Like
For this particular matchup, it's not going to ever be different. It's always going to be 6, because that's like the smallest coefficients that we can get for everything to work out in this particular manner. But if you switched up, if you mixed and matched different half reactions, you'd have to figure out a new N value for that particular pairing. So that does change, unlike our E, which doesn't change. All right, so that was the last leg of our triangle here. You may remember that we looked at this 2 weeks ago or so. So this fills out the last relationship between our Gibbs free energy, our electrode potential, and our equilibrium constant K. Let's say that a redox reaction has an equilibrium constant of 1200. Which statement is true regarding delta G and E for this reaction? Give it a think. Maybe plug some numbers into your calculator, and then we'll find out. All right, what do we think about E and delta G, given this K?
since our K value is positive, but the equilibrium is still positive, energy is still negative.
Our K is positive. K is always going to be positive. The thing that's important about our K, in this case, it's bigger than 1. Or it's bigger than E also, which is like 2. something. It's less than 10. E is less than 10. It's important that it's bigger than 1 for this bottom end, because log k, log of 1 is 0, so that doesn't help. But if we had like log of 0.01, then that would be -2, so that would give us a negative value for our E cell. If the log's something bigger, like let's say it's 1,000, because I don't know what the log of 1,200 is in my head, then that gives us a value of 3. So our E cell is positive. So we can cross off B and D. And then looking at our delta G, negative RT-ln-K, if we had a value that was less than E for natural log of K, then it would be negative, and that would flip because of this negative here. This natural log of K term is positive, meaning that delta G is negative. Hopefully that makes sense. I think that's basically what you said. Just a little difference in the cutoffs, the values we're looking at for K. So we've been looking at standard cell potentials. So that's when our ion concentrations are 1 molar. 1 molar is one of our standard states. We've also got like 1 atmosphere and 1 other units probably. And so for this reaction with zinc and copper, we can tabulate our standard cell potential of 1.10 volts. But how is that going to change? How is the actual cell value going to change when our concentrations change? Let's say that we've got a copper concentration of 2 molar and a zinc concentration of 0.01 molar. It's going to change. So let's see how it changes. It turns out, if we do this at standard conditions where we've got 1 molar, we get, surprise, surprise, 1.10 volts as predicted by our tabulated values. That's assuming that everything goes perfectly. If we change our conditions so they're not standard, all right, so those are the concentrations that we were looking at, what ifing about, we get a higher voltage, 1.17 volts. Here comes the fun slide. There's a relationship between the standard cell potential and the electrode, or the regular cell potential. Knowing that delta G equals delta G naught plus RT-ln-Q, and that delta G naught equals negative NFE. This is also true if you take off the standard state part. So we could also write delta G equals NF E cell. That's also true. So what we're going to do is we're going to substitute in these into this RT-ln-Q. So we get negative NFE sub cell, negative NF E naught sub cell, plus RT ln not K Q, because we're not at standard conditions and we're also not at equilibrium possibly. And we divide everything by negative NF. You don't need to know how to do this, so you can just sit back and enjoy, or be in mental pain, whichever one you want. So this negative NF, to get rid of both of those negative NFs and get rid of those, E cell equals E with that 0 thing, cell, minus RT over NF ln Q. Hopefully that RT over NF ln Q looks somewhat familiar. Imagine that there's a K there instead of a Q. We just saw that earlier today. So we can actually turn that into 0.0592 volts over N log Q. And the rest stays the same. Isn't that nifty? And that is the Nernst equation. So this is another good equation to have. And this relates our reaction quotient Q to our cell potential and our standard cell potential, which will be helpful intermittently. Remember that our reaction quotient Q is like K. It's the same equation as K, but not necessarily at equilibrium. It can also be at equilibrium, but it's not necessarily at equilibrium. Most of the time it won't be. But it's the same products over reactants with their coefficients, excluding gases and solids and liquids, I think. Maybe not gases. Depends. All right, let's get that equation written in here. E equals E with the 0 minus this. There's our Nernst equation without the cells. So we want to determine the cell potential. That's E of a cell based on these two half reactions. And we've got the standard electrode potentials on the next slide. So we've got nickel and nickel 2 plus. We've got VO2 plus and VO2 plus. Let's find those here. Nickel, nickel 2 plus, VO2 plus, VO2 plus. Those should be all the important species. Where's Waldo?
In the middle of the left one. The VO2. Then the top 5 and the right one.
Here they are. Striped shirts and everything. So for VO2 plus, that's the direction that we've got it here. So our E is 1.00. For our other one, it's the oxidation half reaction, not the reduction half reaction, so we're going to flip this negative 0.23. That'll be positive 0.23. So what is our standard cell potential? What? I didn't hear what you said.
Is it 0.77?
It's not 0.77. What's another way we could combine those numbers?
Combine them as balance, right?
Add them together. It's 1.23. The reason that it's 1.23 is that we flipped this top one. So they're already in the way that they're arranged in the correct orientation to pair them up. We've got one is the oxidation, one is the reduction. And so we just add up the cell potentials. If you wanted to do, I believe it's cathode minus anode. You could also do that. We have already flipped the one for our anode from the table. So this cathode minus anode works if they're in the same format, the same positive negative that we see them in the reduction table, our electrode potential table. So if we did it that way, it would be 1.00 minus negative 0.23. So that would be another way to get it. Questions so far? There's a lot more fun to be had. All right, so we've got one piece of our puzzle. We know that E is equal to now 1.23 minus 0.0592 volts over, we need N, and we need Q. We've got one piece of our puzzle, though, so far. What's the smallest number of electrons that we can get when we combine our oxidation half reaction and our reduction half reaction? 2. So the way that we get 2 is we can see in our oxidation reaction we've got 2 electrons on the product side. In our reduction half reaction we've got 1 electron on the reactant side, so we need to double our reduction half reaction. And we also need to combine them. Okay, so the helpful bit of information that we've gotten out so far is 2 electrons. I'm going to go ahead and disperse these 2's. So we're going to have 2 VO2 plus aqueous. I'm not going to write the concentrations down just to save some time and space. And I'm ignoring our electrons as well. So that's everything on the reactant side. We've got our VO2 plus species. We've got our protons. We've got our solid nickel. On the product side, we've got, I wanted to say the liquid nickel. It's the aqueous nickel. Nickel 2 ion. We've also got 2 VO2 positive. And we've got 2 H2O as a liquid. That looks a little too much like an E for my liking. That's not much better. Go ahead and scratch down, scribble down what you think our Q expression is. All right, somebody give me one of the species that's on top in Q. Nickel 2 plus. We've also got VO 2 plus squared. Do we have anything else on the top? We do not have anything else on the top. Water is a liquid. It gets excluded from Q. On the bottom, we've got VO2 plus squared. And we've also got H plus to the 4th power. Nickel metal is excluded because it's a solid. So there's our Q. And we have values. We've got all these concentration numbers. So we get to plug those in as well. So we're going to have our concentration of nickel 2, which is 2 molar, 2.0. Our concentration of VO2 plus, which is 2.0 squared. That's going to be an 8 on top. On the bottom, we've got our VO2 plus 0.010 squared times 1 to the 4th power, which is still 1. So it should be 8 over 0.00010, something like that. We'd put it into our calculator. And then we feed that number into our spot for Q. So 1.23 minus 0.0592 over 2 times log of 8 over 0.01 squared. And our cell potential is 1.08. Questions about any of those parts? This seems like a great short answer question. Lots of pieces to it. Lots of places to give you little bits of partial credit. Hint, hint.
So even though our electrons cancel, it's still 2, right?
It's still 2, yeah. The electrons are always going to cancel, by the way.
So it's just whatever you get for the balanced electrons, I guess?
Yeah, it's whatever you get for the balanced electrons.
And then that's just your anode. Do you think it's easier to memorize just like add them together for E cell, E little circle cell, instead of doing like that E cathode minus anode?
If you know which direction they're going, then you just add them together.
Okay.
If you don't know which direction they're going, like if you're just given a cell diagram, you're not necessarily going to immediately know like, oh, this one's going through oxidation, this one's going through reduction, and know how to flip them. You might be told that this one's the cathode and this one's the anode, and then that's when this E cat minus E anode would be more helpful.
Then is the cathode, it could be either or is it always that one only goes through oxidation?
Red cat,
Red cat.
reduction cathode, and oxidation and anode both start with vowels. That's what we have in the slides, at least. So a relatively involved problem using our Nernst equation. Some generalizations. For a redox reaction within a voltaic cell, under standard conditions, our Q is equal to 1. because our concentrations are all 1 molar under standard conditions. So if you've got a bunch of 1s raised to whatever powers over a bunch of 1s raised to whatever powers, that's always going to be equal to 1. Remember that log of 1 is 0, and so for our Nernst equation, this log Q, this whole term over here turns into 0. So under standard conditions, Q is 1. This whole right term disappears, and so our cell potentials are the same as the standard cell potentials. If Q is less than 1, that means that we've got higher reactant concentrations, since reactants are on the bottom. We've got product over reactant. Reactants are on the bottom. That's relatively going to drive our reaction to the right. So it will proceed. So when Q is less than 1, reaction proceeds right more than our standard state. That's like the conceptual way of thinking about it. That doesn't necessarily mean that it's going to proceed right, but it will do so more than the standard state. Because we could have a non-spontaneous reaction, so it's just more favored to move left to right, even if it's non-spontaneous. The maths reason Q less than 1 means that our log Q is going to be negative. So the negative will cancel with this negative, so our E cell is going to be greater than our standard E cell. The opposite's also true if Q is greater than 1. That means we're more product favored. It's going to drive the reaction to the left relative to the standard state. We'd have a positive log Q here, so our E cell is going to be less than our standard cell potential because of this term still being negative on the right. At equilibrium, our Q is equal to K, and our standard cell potential, not our standard cell potential, I don't think that's supposed to be right. Our cell potential is going to be equal to 0 because it's already at equilibrium. There's nothing left to move. Questions about those concepts? You can get all of that from just using the Nernst equation. You could work your way to those conclusions with the Nernst equation, but it might be helpful to have them explicitly written out. Maybe good flashcard material. In an electrochemical cell, Q is given, K is given. What can you conclude about E cell and the standard E cell? One's positive, one's negative. They're both positive, they're both negative. We've got a guess for A. Other guesses? Why do we think it's A? Q is less than 1. So one thing to think about is how are Q and K related to each other? Q is less than K. What does that mean about our state in Q relative to equilibrium conditions? How does Q get to K? Because that's what reactions want to do, right? They want their Q, the reaction quotient, to move towards the equilibrium constant. We've got products over reactants. To increase our Q value, because Q is less than K, to get our Q value up, we need to make products and or use up reactants. So decrease reactants, increase products. Reaction moves to the right to get our Q to move towards our K. What does that tell us? This tells us that our E cell is positive. Because the reaction is spontaneous. Okay, so E cell is positive. And our standard cell potential, is it negative or positive? So we've got, from an earlier slide, not laser pointer, this. K is less than 1. So log K is negative. N can't be negative, so our standard cell potential is also negative. So it is A.
So to figure out normal E cell without the circle, is it just to see if it's spontaneous or not? Or is it like a mathematical way you can figure it out?
There's probably a math way that you can figure it out. I think relating, seeing how Q would have to move to get to K and then thinking about whether it's spontaneous or not. Like if it moves in the forward direction, then that's going to be spontaneous. If it wants to move in the opposite direction, so if Q is bigger than K, it would want to move backwards. So it's not going to proceed in the direction as written in terms of like thinking about the cell. It's not going to work as a battery. You would have to put energy in for it to work that way.
So then would that be negative then?
Yeah, so that would be negative.
So if it goes forwards, if the reaction wants to proceed forwards, it's positive.
Positive E cell.
Okay.
Backwards, negative E cell.
And then for the E circle cell, you can just figure it out with your K value.
Yeah, with your K value. So how it's, is it bigger than or less than 1? Another thing that we can do, if we're not working in standard states, where everything's 1 molar, is you can do a concentration cell So you can construct a voltaic cell where two half reactions are the same. And all that's different, the reason that we call them a concentration cell, is the concentration. So having a difference in concentration drives the current flow. Our standard cell potential is 0 because it's the same thing, just one's forward and one's backwards. But we can calculate the cell potential. So E cell equals standard E cell minus 0.0592 volts over N times log Q. We already know that our standard cell potential is 0. How many electrons are transferred? Okay, 2. Because it's a 2 plus from a 0. 2 electrons get transferred. Times log, that should be blue, log Q. Q is products over reactants, so 0.010 over 2.0. Ignoring our solids. So 0.0592 divided by 2 times log 0.005. And I forgot the negative sign in my calculator, but you get a value of 0.068 volts. So it's not a lot of voltage, but it is some voltage. And that's just from the concentration. So looking at our concentration cell, if we've got standard conditions, the concentrations are the same, 1 molar on both sides. In non-standard conditions, which we were looking at, we've got difference in copper concentration, and we'll get some spontaneous movement of electrons to get these dissolved copper concentrations to equal out. So we'll have electrons flowing from the lower concentration side to put more of our copper into solution. And on our product side, or cathode side, I guess, these electrons that flow in go to the copper that's in solution. Copper 2 plus comes out of solution. And that will continue to work until the concentrations are the same on both sides. Our voltage is also going to change through time as those concentrations change. Wrong E. Electrons flow from low to high, which is opposite of what we normally think of in terms of anything flowing. Normally it flows from high to low, but in this case the electrons are flowing from low to high because the electrons are what's going to bring our concentrations into equilibrium, to unity. this happens, or things like concentration cells happen in our nerves. I'm not a biologist, so I'm just going to be reading the slides. So you've got little pumps, ion channels, inside of your cells that allow dissolved ions to flow through into the cell or back out of the cell, and that does stuff. So you've got little cell pumps. You can get concentration gradients, so larger concentrations on the outside versus the inside, or inside versus outside. So for example, higher sodium concentration outside, we've got lots of sodium, and more potassium inside, and that can result in an electrode potential, the resting potential of about negative 70 millivolts, so 0.07 volts. If a nerve gets stimulated, the channels open, and that lets sodium into the cell, and that causes a change in potential. So you get an increase in your cell potential, positive 30 millivolts, 0.03 volts. Other channels are going to let potassium ions leave, and the potential is going to drop again. So you get this little spike in your electrochemical potential, a little bit of electricity in your cells. And when that occurs, that can trigger a nearby cell, and it just kind of moves its way down the line with these ions passing between these sodium and potassium channels. So your body can send nerve signals all throughout the rest of your body using processes like this. There will be no questions at this time. So that's just kind of a fun, so you know. And now we get to learn very briefly about batteries and a couple of types of batteries. And we're kind of just going to talk about, here's the types of batteries. So batteries are cool. They're voltaic cells. What's the other type of cell? Pop quiz.
It was on your email, I think. Let's start with the G.
Galvanic cell is the same as a voltaic cell. Electrolytic cell. The electrolytic cell is the one that's not spontaneous. Voltaic cells are spontaneous. So batteries are little spontaneous volt cells that act as portable sources of electricity, as you know. The type of reaction that occurs depends on the type of battery. So one type of battery is a dry cell battery, called that because there's not a lot of water in it. They do contain a little bit of water because you kind of need a little bit of water in there. So as an example, you could have a zinc half reaction with this manganese 4 oxide half reaction and some ammonium. If you combine these two half reactions, cross out the electrons, 2 MnO2 plus 2 ammonium plus zinc metal goes to zinc 2 plus manganese 3 oxide, 2 ammonia, and a little bit of water. That would be our overall reaction. I'm just assuming that we can combine those things. So the way that it works is you squeeze in a paste of the MnO2 and the ammonium chloride. You've got a zinc case. So the zinc, here it is a solid. So that's in there as a solid, and it will get pulled into solution as our reaction occurs. So it turns into zinc 2 plus. We've got a graphite rod in the middle, and then terminals on two ends. And that works. These two half reactions produce a voltage of 1.5 volts. which is pretty standard battery voltage for like double and triple A batteries. I think they're primarily 1.5 volts. If you connect them in series, that produces higher voltages. So the reason you have to throw multiple batteries into devices is because they need more than 1.5 volts. So they connect them in a series to get the required voltage that they need of whatever is greater than 1.5 volts. There's also the one that we're more familiar with, a type of dry battery, alkaline batteries. Alkaline like basic. And that's because they have a basic medium. A little fortune teller that likes Starbucks. I got 2 laughs. That's good enough for me. So zinc, metal, we still have our manganese fluoride. We've got hydroxide, and we've got some slightly different products. It works pretty similarly. We've got our paste. We've got an anode on the outside, a cathode on the inside, and we've got some terminals. And we can cross stuff out. We can cross out our hydroxides and our electrons, and we can combine those. And these are apparently better than regular dry cell batteries, which is why we use them so much. Questions about batteries so far? Notice that it's basically the same half reactions. It should be the same volts. Another type is lead-acid storage batteries. This is what's in most cars, or conventional cars, because not all cars, hashtag not all cars. Conventional car batteries have 6 cells that are wired in series to increase the voltage. So 6 cells of 2 volts gives you a total of 12 volts, which is your standard car battery. Your standard car battery, 12 volts. And these have lead, that's the lead part of the lead acid, and acid, the acid part of the lead acid storage battery. So if we combine these, we have to 3x this top equation. No, we don't. Just kidding. Psych. Because our electrons cancel. We can cross stuff out. So we've got lead plus 2HSO4 minus plus PbO2 plus 2H plus goes to 3 lead 2 sulfate plus 2H2O. So the lead acid storage battery that's likely in your car, unless you've got an electric vehicle, looks something like this. You've got an electrolyte, about 30% solution of sulfuric acid. You do have to have water in your car battery. If your battery is dead for some reason, it's possible that your lead acid battery dried out, because that will happen. So you need to make sure that you add some more distilled water in there. Make sure that it's distilled, and then maybe it'll take a charge again. So sometimes you don't need a new battery, you just need more water in your battery, which is surprising. And it's also got sulfuric acid in there, so be careful when you're adding the water, and this is also part of why you need to dispose of these in a certain way. Okay, so both of these electrodes produce lead 2 sulfate, which can coat the electrodes if it runs for too long. If you recharge it with an external current, like from your alternator or from a trickle charger or something, then that can reverse the reaction, and then you get some more life out of your battery. You can also, I think for some of these types of batteries, sometimes if they're not working, you can kind of like hit them with a really high voltage and like shock life back into them, but that's not advised under normal conditions. So if it's running fine, you don't need to shock your battery. And you also don't have to worry about getting shocked by your battery because it's only 12 volts. There's also NiCad batteries, nickel cadmium, that's a rechargeable battery, where you've got solid cadmium that's oxidized to this, and the nickel part that gets reduced to this thing and produces an overall voltage of about 1.3 volts. Just like with our lead acid battery, you get a buildup on the electrodes, but if you run the reaction in the opposite direction, then it refreshes the reactants. So when you're charging it, you're running it backwards. You're just running your battery in backwards mode. So that reverses the coding. So just run your battery in backwards mode, switch it to wumbo, and you should be good to go. If you overcharge it, or just over time, some unwanted reactions can occur that damage your battery. There's also NiM, nickel metal hydride batteries. I don't know if they're actually pronounced NiM, but you've probably also seen these if you've been around for a bit. Nickel cadmium batteries are being replaced because of the toxicity of cadmium, so they're not as popular anymore. Nickel metal hydride, a little bit more recent. I think within our lifetimes they've become popular. It's a different anode reaction. So swap out cadmium to a metal hydride. And the metal hydride part is our hydrogen atoms are held in a metal alloy. And because it's a metal hydride and it's the hydrogen atoms instead of the cadmium atoms, you get better energy density. And then the newest, which these have been around for a long time now, but the newest and the most expensive, lithium-ion batteries, which are now pretty common. And lithium-ion batteries have really high energy density because lithium is small. Common in lots of devices. And you get fun stuff that happens with lithium. So kind of all that you need to know is batteries exist, and there's a couple types. I don't expect to test you on like how do they work, what's the reactions. There's
To know what types?
I will probably at most put a single question. If I put a question, it'll be one question about types of batteries. Which of these is like a type of battery? And then you just pick all of the above or whatever. There's also slightly newer, these are becoming a little bit more popular, fuel cells. So fuel cells are like batteries, but your reactants, your fuel, needs to be constantly replenished, so you have to pipe in your reactants. The hydrogen-oxygen fuel cell is the most common. So you'll take H2 gas, flammable, O2 gas, also flammable. You run the H2 gas past an anode, a screen with a platinum catalyst, and that gets oxidized. The oxygen gas, which you could get from the environment, flows past the cathode and gets reduced. And because we're combining H2 and O2, water is our only product, which is great for the environment because then you just have water coming out of your vehicle instead of also CO2 and other combustion products. However, you can imagine that there might be some issues if you put cylinders of compressed hydrogen and oxygen into your vehicle. If you get in a car crash and one of those ruptures, goodbye. So that's why we don't have these running in vehicles because one crash and that's it, versus gasoline, which will also explode, but not as spectacularly most of the time. Here's an example of what a hydrogen-oxygen fuel cell might look like. So you've got our hydrogen coming in on one side, we've got our oxygen coming in on the other side, we've got some electrolyte where the reaction can take place, and boom, bam, magic, electrons get produced. This is also apparently used in some types of breathalyzers. So one type of breathalyzer uses a fuel cell to measure the quantity of methanol in the breath, which is proportional to the amount that's in your bloodstream. You can smell alcohol on people's breath. Since I stopped drinking, my skill at smelling alcohol on people's breath has gone up significantly. You can smell it. It's there. If you're around people that drink, you can smell it. And the breathalyzer takes advantage of the fact that that's a proportional amount in your bloodstream with how much is in your breath, because it comes out through your wherever. So you pipe in your breath, presumably with some alcohol in it, and it undergoes a reaction and produces a little bit of a charge. And you can, if you calibrate it well, then the amount that comes in corresponds to a certain amount of charge, and then you can correlate that to a blood alcohol level. I think 0.08 is really high. So it'd be bad stuff. And again, if you calibrate it, if you don't calibrate it, it is less effective. But if you calibrate it, then it works really well. And you can tell how much somebody's had to drink if you suspect them of being a drunk driver. Or if you just need to start your car and you got one of those breath locks or whatever. Okay, I'm not going to do the balanced reaction. We'll start with electrolysis next class.